Good morning. Thank you for getting up so early. Perhaps the parties weren't so good last night after all. So this is the first of the Khronos BOFs today, and we're starting out with a number of the APIs that we can use for vision processing and neural net inferencing, which is an increasingly hot area in the industry. So we're fortunate to have a number of speakers that can talk authoritatively about the APIs that we're doing. Myself, I'm Neil Trevitt. I work for NVIDIA. I'm also the Khronos president and I'm the OpenCL chair. So I'm going to be talking briefly about OpenCL. We have Ralph Potter from CodePlay, who's going to be talking about SYCL, which is a C++ single source framework that builds on top of OpenCL. And then we have Peter McGuinness, who is chairing the NNEF working group. NNEF is Neural Net Exchange Format. And then Radha from AMD, who's going to be talking about OpenVX, which is vision acceleration. So if you haven't come across Khronos before, you probably have because you're here. But we're an open standards consortium. We have about 140 companies right now that are come together under a single IP framework to cooperate to create open standard royalty-free runtime APIs and file formats. We focus on the interface between software and silicon. So we typically do runtime APIs for the hard stuff that you need silicon acceleration for, like 3D graphics, obviously, but also parallel computation, increasingly vision and neural net processing. So we have quite a few APIs around the vision and neural net space. It's fast evolving and quite a complex space. So we thought we'd kind of start by just showing how the various APIs kind of fit together. If you wanted to use Khronos ecosystem APIs for the grand challenge of vision and neural nets, and how do they fit within the ecosystem. So if you're using neural nets, and neural nets obviously haven't replaced traditional imaging, but probably 70% of what we used to do with traditional vision processing now is being done with neural nets. The first stage is to train them. Training typically takes place on high-performance desktop or cloud hardware, and we have two GPU acceleration APIs, OpenCL and Vulkan. Increasingly, a lot of the training frameworks are being written in C++, so SYCL, that Ralph will be talking about, is a good fit if you want to accelerate C++ authoring frameworks. Once you've trained your framework, you want to bring that trained data over to the runtime system. It might be a small embedded device, it might be your car, and we have NNEF, which is the neural net exchange format, that lets you encapsulate a neural net, the topology and the weights, and bring it over to inferencing hardware. And then we need the vision application itself running on the device that you want to deploy. OpenVX is a high-level API. It gives you a graph abstraction, so it's easy to program. It's very portable. SYCL, again, if you have libraries and vision software written in C++, SYCL can be a good way to get to OpenCL acceleration. And then, again, if you have low-level access to the hardware, you could use Vulkan if you have a GPU, OpenCL if you have a GPU or heterogeneous hardware. So these are the APIs that we're going to be covering today. Let me start with just an update on OpenCL. So OpenCL, if you haven't come across it before, is a low-level parallel programming framework. You have a couple of APIs, you have the choice of a couple of kernel languages, C and C++. So you take the code that you want to run in parallel, you write it as a small kernel in OpenCL C or C++, and then you use the APIs to interrogate the hardware, compile those kernels for the hardware you want to run them on, get them to execute in parallel across your hardware resources and gather back the results. So the key to understanding OpenCL is it's very low level, which can be very good or very bad, depending on the kind of programmer you are and the kind of thing you want to do. But if you need low level control. You want to be in control of what runs where. OpenCL will give you, that granularity of control over your system. So we just have released a new version of OpenCL, OpenCL 2.2. Was released in May 2017, so just a few weeks ago. And this is something that we've been working towards for a few years now. C++ from kind of top to bottom. SYCL is single source C++, but in 2.2 now we have the choice of running C++ as the kernel language. Before, we were limited to C. And the key technology piece that enables that is SPIR-V, which is the Khronos-controlled intermediate representation that understands parallel computation and graphics rendering. So now we have SPIR-V 1.2 ingestion in core, and that gives us everything we need in the OpenCL runtime to run C++ programs as kernels. As well as the new spec, we've actually changed the way that we're engaging with the community. We've put the specifications in open source. What that means is all the source materials, all the ASCII doc files that we use to build the final OpenCL specification is now uploaded onto GitHub. That means you can actually go and mix and match your own specification if you want. If you use a subset or you want to translate it or do anything you want, it's under Creative Commons, so you can use that material to create your own internal or external documentation. We've also put the conformance tests into open source for the first time. So any implementer of OpenCL can download the conformance tests, run them on their implementation, to make sure that their implementation is running correctly. We still have the adopters program. If you want to become officially conformant and use the trademark and enjoy the protection of the IP framework, in other words, the Khronos members won't sue you over your implementation of OpenCL, then you become an official adopter and pass the conformance tests. But people can try out their own implementations at any time with the tests now are on GitHub. We also, we've had these for a while, but we're kind of revving them up. We want to have deeper engagement with the developer community. We have things called advisory panels. It doesn't cost that much to join Khronos. If you're working for a company, it's $3,500 is the entry price for smaller companies to join Khronos and get full access to everything. But even if that's too much, we have Khronos advisory panels where we invite folks who want to contribute to the roadmap and specifications. And they don't get to go to the working group meetings, but they come under the IP framework and the NDA. So we can share draft specifications with the advisory panel, which we do on a regular basis, get requirements into the design process. And coming onto the advisory panel is free. So if you're into wanting to influence where any of these specifications are going, and membership is just a little bit too much, talk to us about becoming a member of the advisory panel. We'd love to talk to you about that. And we have advisory panels for Vulkan, OpenCL, SYCL, and NNEF is building their advisory panel right now. So the OpenCL ecosystem, we have lots of hardware shipping, desktop and mobile, and increasingly embedded. And a lot of the applications that ship, mainly on desktop right now. I think that desktop is the hot spot for OpenCL deployment. We have like Adobe, Photoshop, GPU acceleration is based on OpenCL. Halide, it's called image processing library, Otoy, high-end rendering, all the Sony Creative Suite, Mathematica. A lot of the TensorFlow Cafe, the neural net training frameworks, OpenCV, kind of goes on and on. We have a bunch of stuff that's now using OpenCL, primarily on the desktop. And it's interesting to see how the hardware, classes of hardware deploy OpenCL. So going right back to 2008, almost 10 years. Hey, we need a 10-year birthday party. So the chips tends to ship first on the desktop. And Intel have just shipped 2.1, and the spec for 2.2 is shipped, so that pipeline will continue. The mobile guys are actually doing pretty good. They tend to ship a year or two later, but we have now multiple mobile vendors with 2.0, and the first mobile vendor has just applied to become an adopter for 2.1, so that pipeline is continuing too. OpenCL is used by FPGAs, because it's OpenCL 1.0 gives you a way to program FPGAs and software rather than doing it like VHDL type design. So that's becoming increasingly popular. And a big development, I think, is the embedded space. DSPs, particularly for vision and inferencing, are getting sophisticated enough. They need a OpenCL class runtime programming environment. And the first DSPs are beginning to appear with Conformant 1.2. I mentioned that OpenCL is used for a lot of applications on the desktop. Actually, what we're seeing is OpenCL, as well as being used directly by an application vendor, is being used by middleware very often as a compiler target for things like Halide, OpenCV, and the neural net training frameworks. And we have now hundreds of languages and frameworks, over 4,000 GitHub repositories of projects using OpenCL applications, like languages, libraries. And that's a pretty good growth. From 2 years ago, it's grown by twice. So we had 2,000 2 years ago, and now we're up to 4,000. I'm going to talk very briefly about Vulkan, because Vulkan is part of the OpenCL roadmap discussions that we're having. For those of you not familiar, I'm sure most of you are, Vulkan is the new generation of 3D API, where it's much more explicit. It actually has become more like OpenCL in a way. OpenGL had a really thick driver, lots of heuristics. Your driver is trying to isolate you from hardware. Vulkan, a much thinner driver, like DX12, that lets the application programmer get closer control over the GPU hardware. Now, we no longer have a universal API. OpenGL ES 3.0 was the last API that was available on every system in the universe. And then Apple didn't ship ES 3.1. And now Apple have gone to Metal, and we can't ship Vulkan natively on any of the Apple platforms anymore. And that's a problem for the developers. It can double or triple the back-end porting costs if you want to hit all of the platforms, PCs, Android, and Mac. So at GDC, which was back in February, we went out to the developer community and said, do you need us to fix this? And yes, please help us. So we said, well, shall we create like an amalgam API, a portability API that can run anywhere? And we got the very wise feedback from the developer community, which was, please do not create a fourth API. 3 APIs is bad enough. Fourth would be even worse. It's more fragmentation, which was, of course, the right answer. So what we took that feedback and reconsidered what we were going to do, and we came up with the idea of defining a subset of Vulkan that can run everywhere. So we have the games engines, native apps. If they could write to this subset of Vulkan, it can be directly and efficiently mapped to the underlying APIs on the systems like Metal and DX12. So that's the process that we're in now. The Vulkan Portability group is a subgroup of Vulkan. We're working within the Vulkan working group where we're doing this API analysis. And the overlap is actually quite good. That's the good news. That's why I think this is a viable thing to do. That overlap is like 85% plus. You lose some of the crinkly bits around the edges of the APIs, but the bulk of the API is there, and it'll run efficiently. So if you want to trade that last optimization opportunity for portability, I think this might be an interesting path forward. So the intent is to have a bunch of open source tools. We'll have an API library that converts the API calls to the underlying native API. We already have SpearV Cross, which is an open source translator from SpearV to Metal and HLSL. So we can take a Vulkan program and take it into Metal and compile it through the normal Apple compiler chain. We want to do a layer that will detect if you're using API calls that fall outside that overlap. Someone suggested to me yesterday we call that the Metal Detector, which I thought was a good idea. And we have a subset of the conformance tests, so you actually check that things are working. So there's some open source work to do here. There's actually already an open source project, GFX RS, that has identical goals, and actually it's by folks from Mozilla who are in the working group. So you can come and start helping us, both on SpearV Cross and GFX RS. So what does that have to do with Vulkan? So Vulkan, we're at 2.2. As I say, we've been working towards C++ top to bottom for a while. So we're kind of like at a crossroads now. What do we do next? And we've had a lot of discussion at the working group. And we've come up with three kind of projects, three directions we think we want to go in. One is based on SYCL, and Ralph is going to talk a lot more, but all of these C++ projects like SYCL and CUDA and C++ AMP, the long-term goal would be kind of cool if the standard ISO C++ had the necessary machinery for parallel programming, and it was just standard, and we didn't have to create variants of C++ or use C++ in weird ways. And all of those groups, I think, are kind of working at ISO towards that larger goal. That's a longer-term goal. That probably will take, 10 years or something. But it's a worthy goal that we need to work towards. There's another project, realizing that DSPs in the embedded space is becoming increasingly important for OpenCL. There's a bunch of DSP vendors that want to be conformant, but OpenCL kind of has this desktop mentality, and we mandate IEEE 32-bit floating point, which is not relevant to a lot of the DSPs. Some of them can run. Those TI and Marvell DSPs now have that. But there's a lot of smaller DSPs that, particularly for vision and inferencing, that are 8, 16, 4-bit for inferencing. So we're kind of locking them out with insisting on IEEE 32-bit floating point. So we want to do a DSP profile as quickly as we can to bring those DSPs into the fold. And then last but not least, Vulkan is shipping in places that OpenCL can't reach, and many applications need an integrated runtime with graphics and compute. For those of you who went to some of the SIGGRAPH sessions yesterday, people talking a lot about compute within the graphics pipeline. Vulkan obviously will evolve its compute capability, and we want to bring the learning and experience of OpenCL to help that evolution of Vulkan compute as rapidly as we can. And that's actually started this afternoon in the 3D BOF. There's going to be a lot more detail about this. CLSPV is an open source project by CodePlay, Adobe, and Google. It's an experimental compiler right now, but it's already been used to process Adobe's production OpenCL code. Turns out they have 200,000 lines of OpenCL-C. The compiler lets you compile that into Vulkan runtime, SPIR-V, and run it in the Vulkan runtime. And it's using some of the extensions that have come into Vulkan as a result of people in OpenCL kind of pushing the compute capability. So going forward, for a class of people that want compute in Vulkan, and Vulkan can be universally available through the Portability project. Vulkan, for many devices, can provide universal graphics and compute everywhere. So for some folks, that's going to be interesting. All right, so that's the OpenCL update. Let me hand it over to Ralph.
Hello, everybody. So I'm Ralph Potter. I'm a research engineer at CodePlay, where I generally work on programming models for heterogeneous systems. And today I'm going to talk to you about the state of SYCL and the things that we've been working on recently. So if we start with what is SYCL, it's a high-level C++ abstraction layer for OpenCL. We have full coverage for all of OpenCL's features. So if it exists in OpenCL, somewhere in the C++ abstraction, there is some corresponding API that allows you to do the same thing. We also have interop features. So if you have existing OpenCL C kernels or existing OpenCL code, you can still make it interact with SYCL in a useful way. And when I talk about SYCL, I think it really provides two important things. The first it provides is single source compilation. So we can put our kernels and our host code in the same source file. We can kind of easily share data structures between the two. That's the first part that I think is really important. The second part that it gives us is SYCL gives us an automatic scheduling of data movement, basically for free as a side effect of its programming model. So because of how you define kernels in SYCL's programming model, it gives the runtime enough information to know when it should be moving your data from the host to a GPU or from one GPU to another GPU. On top of which, SYCL is designed to be entirely standard C++ code. So your host code you can put through any compliant C++ compiler, and then your device code you put through a special compiler that generates some kind of binary that's suitable for your accelerator, whether it's SPIR-V or whether it's something else. So just a quick example. This is pretty much the hello world of SYCL. This is enough to get you your data onto the GPU, to double every element in a vector and get your data back off the GPU afterwards. Essentially, all we're doing here is we create a device queue, which in this case is choosing a default device. You can parameterize that to choose something else if you want. We create a couple of buffers, which are essentially taking ownership of your data for that buffer's lifetime. And then we have this submit statement, which is submitting work to a queue, but crucially, at the same time as it's submitting a kernel, it's also submitting the access requirements for the data that we're going to use. So we're saying one of these buffers we're going to read from, one of these buffers we're going to write from. And that's important because it allows SYCL to build up its dependency graph. So when we look at how SYCL fits into the ecosystem, essentially OpenCL is our bottom layer. OpenCL is providing all the compute work for us. SYCL isn't directly interacting with a hardware driver, it simply interacts with an OpenCL runtime. SYCL sits above that, providing the C++ abstractions, managing the data movement and that sort of thing. And then your application might address that directly, or it might address it through a C++ template library, something like Eigen for linear algebra or TensorFlow for machine learning. So one of these key points about SYCL and how it manages your data movement is we're separating storage and the characteristics of your access. So you have some data, you wrap it in a buffer, and that, once you've wrapped it in that buffer, that's going to manage whether the runtime puts that on a GPU, whether it leaves it on the host, whether it needs to move it around. And it does that by using these accessors to describe the access that you're going to require to the data in a specific kernel. And those accessors are referenced in a command group. A command group is like an atomic thing that says, for a particular kernel, I have this set of access requirements, so before you run the kernel, you must satisfy those requirements. And that might be scheduled on a CPU or a GPU, depending on what queue you dispatch this command group to. Buffers and accessors also give us very strong type-safe access between the host and the device, because everything is all in one source file. The compiler can see everything. It can ensure that the thing that you're referencing inside the kernel is the same definition as the thing that you referenced in the host code. So this whole system allows us to build a dependency graph of tasks. So given a set of command groups and a set of buffers, here our first command group, we're going to read some data from buffer A, we're going to write to buffer B. The second command group is also going to read from buffer A, but is going to write to buffer C. So we can see these two are not dependent on each other, and a scheduler should be able to identify that. And then we have a third command group, a third kernel, which depends on these intermediate results that we've calculated. So that's obviously dependent on command groups A and B. So this is what the SYCL runtime is doing internally to manage the movement of your data and to make intelligent decisions about where to put it. So we've covered a lot of this, but the dependency graphs allow you to describe your problems in terms of how kernels relate to each other. It frees you as a developer from doing all the data movement yourself. Now, if you've already built an OpenCL application, you probably already have something that does this data movement. But if you're starting from scratch, we can do all of that for you. And the runtime can be very intelligent about knowing exactly when to move data and exactly which OpenCL API calls it should be using to put your data in the right place. Should it be mapping buffers? Should it be enqueuing copies? That sort of thing. So Neil mentioned earlier that we have a C++ kernel language and SYCL, and that sort of suggests that we have two approaches to C++ here. And they offer you slightly different things, and I'd argue that which one is more suitable depends on where you're coming from and on your kind of problem domain. If you already have an OpenCL application, and you've done all the scheduling work, you've done all the host API work, you've already written some of your kernels in OpenCL, but you'd like to use some C++ and some templates inside your kernels, then maybe the kernel language is the easier route on in that case, because you've done a lot of the work anyway. But there is a constraint that the C++ kernel language today allows you to use templates within your kernels, but doesn't yet allow you to template a kernel. By contrast, if what you're starting with is a really template-heavy C++ library, but you haven't done any of the OpenCL stuff yet, then maybe SYCL is an easier route in. We can handle a lot of the complexities of data movement. We can do that very efficiently. We can provide something that's much easier to integrate into a template library because we can handle these shared data structures, which are not easy to get into the kernel language in certain cases. So if you're coming from that side and your application is already a heavy C++ template library, again, like Eigen or TensorFlow or something like that, then maybe SYCL is an easier route in, especially if you're wanting to do things like expression trees and really complex template manipulation. So Neil also referred to the fact that we're converging with ISO C++. So all three of these compute languages have representatives on the ISO group. All three of them have people contributing work to do with heterogeneous C++. Khronos has a project where we host an ongoing implementation of C++'s parallel STL, which just allows you to call STL functions but direct them to an OpenCL device. Members of the SYCL working group have put in several proposals recently to do with enabling heterogeneous compute to ISO C++. So executors, which is really about scheduling work and is not necessarily about GPUs today, but is a necessary stepping stone to getting work onto GPUs in the future. It's mainly about saying, I have a piece of work, schedule it here or here or here. We also put in a position paper in the last C++ meeting about data movement for heterogeneous compute and the problems that you have to solve, mainly to inform the C++ standards organizations about the sort of problems they're going to have to think about to get heterogeneous compute working. Manage pointers and channels, again, largely derived from the work in the SYCL group and are to do with sharing data and data movement. You can think of them as being fairly tightly related to SYCL's buffers and accessors. We're hoping to get some things in for C++ 20, but the timescales are really tight, and there are some really big issues to do with differences between C++'s abstract machine today and certain assumptions that OpenCL and the other heterogeneous compute APIs make, which need solving. So that's going to be pretty hard to hit. So let's call that one a hope rather than a promise. I hope that's not me. Okay, so I'm going to talk about 3 ongoing projects that make use of SYCL today. The first one is parallel STL. So Khronos is hosting an implementation of ISO C++'s parallelism STL. This allows you to take standard template library algorithms like sort or transform or for each, and by passing an execution policy which you can configure to run on a particular device, you're saying, do my sort on a GPU or apply this transform on an OpenCL processor. So it's a very simple way to get some OpenCL acceleration just by changing one parameter of a sort or of a transform function. Next up from that is our work on the Eigen linear library. So this is primarily focused on TensorFlow on tensor support for machine learning and neural networks. So today we have equivalent coverage in the tensor module, at least, to CUDA, and we're currently working on optimization for various hardware architectures, be it OpenCL CPU or desktop and mobile GPUs. So the code for that is already mainline in the Eigen repositories, and we have engineers doing ongoing work to optimize that. Similarly, for TensorFlow for machine learning, we also have SYCL backend support. We have most of the major CNN operations. In fact, I think all of the major CNN operations. So we have complete coverage for a lot of the big image recognition networks. We can run the whole thing on top of SYCL. There are various less commonly used operators that we haven't got to yet, but there's ongoing work from engineers at CodePlay again, and at other places like Xilinx and Intel China to get additional operators in and to get optimization for various architectures. And both Eigen and TensorFlow are a good example of cases where SYCL helps a lot in that they're using very complex combinations of templates to fuse sequences of operations into single kernels, which gives great performance. But if you want to do that in OpenCL C, you have to do it by dynamically constructing a kernel through string manipulation and that sort of thing. So just to wrap up, SYCL gives us a single source programming model where we can use standard C++. We can express kernels as lambda functions or C++ functors, and it's all layered over OpenCL, so we get OpenCL compute performance, but with a nice, convenient C++ programming model. We get the benefits of things like kernel fusion by being able to make use of the C++ template system. And if you'd like more information, then we have this SYCL Tech website where we're kind of posting news and updates on the whole ecosystem as we go along. So with that, I'll pass over to Peter to talk about NNEF.
Okay, I think we're ticking on through the time, so I'll be really quick. There's not a huge amount to say about NNEF. It's a relatively new effort. NNEF, as Neil said, stands for the Neural Network Exchange Format. And what it is an attempt to unify the way that we exchange data between neural network training frameworks and the inference engines. What we've got at the moment is this situation that's in the top half of this slide here. Every framework outputs its own format. If you want to import that into an inference engine, it's probably got its own preferences. And you have to write a translator for each route. So NNEF is trying to bring about a little bit of order to that situation to produce some interoperability where any framework can output in the NNEF format, any inference engine can import from that format, and so that simplifies the whole transfer process. So you can think of it, if you like, you can think of it as a kind of a PDF for neural network descriptions. PDF just describes what you want in the document. The implementation of that description is up to the implementer, but everybody can read that format. That's the objective with NNEF. So it's purely a way of getting data in a standardized way from frameworks like Caffe or TensorFlow or whatever, and into the inference engines. And the objective is really to import into inference engines in a mobile environment. So what we want is we want to enable a very lightweight transfer, and we want to enable the implementation of efficient engines in hardware, probably. So we've got a kind of a sub-objective of the group is to operate well with the OpenVX inference, the inference part of the OpenVX API, so that we can create a tool flow that goes through these two Khronos standards to the inference implementation. So yeah, it's written down there in red. It's a cross-vendor neural net file format which encapsulates some semantics for describing your network. It can describe the structure of the net, and it also carries the parameters in the same format. So you've got everything that you need to implement in your inference. One of the things that we've done with the format is we stayed away, deliberately stayed away from being prescriptive about things like the operations that are encapsulated in the syntax. So we'll tell you that you need to do a convolution, but we won't tell you how you need to do it because that's an implementation detail. And what that does is it allows people to optimize operations for their specific implementation. We don't want to tell people, you must carry some floating point in your DSP in order to do this, in order to run this network. We want to give people the opportunity to say, okay, I have a DSP, which is very efficient. It has 12-bit, some sort of 12-bit fixed point implementation. They can import the net using NNEF. They can cast that using one of their internal tools into the optimized format. They could be using libraries written in OpenCL, for instance, which are implemented as kernels that they're running as part of an OpenVX graph. But the NNEF format doesn't mandate that they have to have any specific operational characteristics in their implementation. It leaves them free to make that optimization. So this is the kind of a usage flow. This is more a statement of intent than where we are right now. We want NNEF to be usable as an authoring tool, so we want people to be able to write it as an input to the training framework. So the syntax is kept very simple. It's hierarchical. You can write the network in quite a compact form and import that into a training framework, if you like. The second point there, between the training frameworks and the inference engine, that we assume that this is going to be automatically generated. So it's not so important that the code be, or the format be human readable or human authorable at that point, but we still want it to be efficient. Where we are right now is we're aiming at that central part of the tool flow. So the first proposal that we have, which is going to go hopefully by the end of this year to standardized, what's the word I'm looking for? Provisional, standard 1.0 provisional, that will be aimed at that part of the flow. And what that we hope will enable is transmission from training frameworks to inference engines, but also it'll enable the creation and use of third-party tools or vendor-specific tools where you can retrain and re-optimize networks, and you can exchange backwards and forwards using this exchange format. So right now, version 1 is under development. We've decided we need a provisional stage where we can gather industry feedback. Neil commented that this is something that we're doing more and more. It's proven to be extremely valuable. What the provisional spec does is it gets something out there. People can use it. They can be reasonably assured that when the full spec comes out, there are not going to be any massive feature innovations in the full spec. There'll be some detailed changes based on feedback from the industry, but it does get people, gives people the ability to start using the standard before we cast it in iron and say, right, this is the final format. So as part of that, but before we reach the provisional standardization stage, and starting now, we've got the advisory panel. We've got quite a few participants. Everyone's invited to participate. What the membership of the advisory panel gets you is it gets you the ability to see the standard as it's written today. So if you were to join the advisory panel today, the cost is, financial cost is zero. The commitment is an NDA commitment and an IP commitment. You can join either as a company or you can join as an individual. Obviously, as an individual, if you join, you have to be, your company has to be okay with that, and you're not allowed to operate as a member of your company as an individual member. But that does give you the ability to join in a kind of a lightweight fashion, and that's usable. That's very usable. That's very useful for academics who don't want to drag their university into the whole mix. Okay, so where we are now, we're focusing on the interface between the framework and embedded inference engines. That's that middle part of the diagram I showed you. We will allow training as a secondary goal. The way that we are right now is we're not excluding the possibility of training, but we haven't focused on that as a primary objective. We have a wide range of network types that are supported, but networks keep on being developed, so we keep on having to add them. That'll be an ongoing thing. So our objective is to track the development of new network types. We want to bring in authoring and retraining. This is not for version 1, this is for a subsequent version. And look at a wider range of applications which are outside of vision. Right now we're working very closely with OpenVX in the vision field, but it has applications outside of that. And then just expand the capabilities of the syntax to increase its expressive power. And then there's a shout out to the companies who are working with us. One company that I should give a particular mention to is AI Motive. They've provided the spec editor, so Victor Guinness, and he's done a huge amount of work on this, so we have to thank them. And I think that is it.
Okay, now we move to the vision acceleration. I'm going to just go over the quick overview of the overall ecosystem that we have and key features of the OpenVX. To go to the real technical details, it's going to take a long one, so I'm just going to quickly browse through some of the concepts that we kind of use to build the spec. So at a high level, when we started looking at the OpenVX problem, we wanted to come up with an API that people can use to express the vision pipeline, that vision processing pipeline that they have, to be able to express it at a high level without having to worry about how it gets mapped to underlying hardware. The use cases of vision, especially, is if you try to look at it, there's a whole set of processors ranging from multi-core CPU to GPU, maybe hybrid of both, and there are vision processors, there are DSPs, and there are dedicated hardware. So we want to come up with an API where user application developer don't have to worry about how actually the work gets scheduled, but they want to be able to specify the functionality, what all the functionality they want, the whole vision pipeline from end to end in there. And one approach we took that is to be able to specify that in a graph way, in a kind of graph-based approach, and specify each function as a node, and a node that is people are very familiar with, things like, if you have a Gaussian filter, you specify what is the size of the Gaussian filter you want, and if you want certain feature detectors such as, let's say, Harris filter, Harris corner detector, you specify that. If you want an optical flow, there's an LK optical flow that is quite popular, you just specify those functions. And then you specify them as each node and then connect them, saying, okay, where the data is going to go. And when you also specify, you can specify, I think SYCL uses the word accessor. Here you can specify how a data being used, read or write. You can also specify whether it is something that an application wants to access it, or is it something like an intermediate. So the way that, the fact that application specifies at a high level its intent of what's the whole compute end-to-end is, it gives a platform vendor to look at the whole graph and then say, okay, how do I map it to my own hardware, independent of whether it's a DSP or CPU or a GPU. They map it differently depending on the hardware. And that's the essence of the whole thing. And couple of the key features, I think a lot of them are similar to other specs that we have. We wanted to get the portability, not just functional portability, also have performance portability. So what do we mean by performance portability? Is not that you get the same amount of milliseconds time on every hardware. It's just that whatever is the theoretical performance of the hardware that a vendor claims, vendor has an ability to take this description and map it and schedule it onto their particular hardware to get the peak performance that's possible without an application having to go and say, okay, now put this in this particular cache or tile it at a particular way. So application doesn't have to worry about it. So once you write an application, it'll just scale well across all different hardware. And also another one we had was a goal of having a power portability, right? That is key in embedded space. For example, if you specify your end-to-end application and you have a graph that doesn't make use of certain hardware, underlying platform, since it looks at from end-to-end pipeline, it can turn off certain hardware blocks. So you have that kind of a flexibility for a vendor to do those kind of optimizations. Right? So that's OpenVX at a high level. Now, I talked about graph level abstraction. So the way to think about it is you specify each function as a node. So here is a simple example. Imagine you have a data coming from a camera, and it is an RGB image. Now, all you care about is processing in grayscale, for example. So you need to kind of specify that you want to do a color conversion and to a YUV space, because all you want is a grayscale. Try to see which color space has a grayscale. You can say, okay, I'm going to put a color conversion node, get a YUV. I want to just extract the Luma channel out of it. I'm going to use that as my starting point. And then after that, in this particular example, it does a Gaussian pyramids and uses that in optical flow. And sometimes optical flow, when you keep running, after some time, you lose the key point, so you want to kind of refresh it using some kind of a Harris corner detector in the middle to kind of refresh it. So you can kind of specify the whole pipeline from end to end as a graph. And now you could leave it to the hardware to figure out, look at the whole graph, figure out how you're going to optimize it. There are various ways. An implementer will look at it. There are certain things, for example, if you look at the color conversion like channel extract, an implementation will look at it and say it can fuse it. It doesn't even have to generate some of the intermediate data, for example. Chroma channels that are used in the color conversion, it doesn't even need to do that conversion. It might directly jump from RGB to directly grayscale conversion, things like that. We'll get a couple of more examples later. Now, how does, I touched upon a few of these earlier. How does a vendor, how does basically OpenVX get the performance out of a graph? Now, first one is scheduling. It can look at the whole graph and say which functions map well into the underlying hardware. So if you have a system that has both CPU, GPU, some kind of an ISP, or if you have a system that has DSPs and some kind of a host processor, it can look at the graph and figure out which parts go well into the hardware, each block of the hardware. And that is very specific to a vendor who implements OpenVX. So, and that's the first level of optimization one can do. And this optimization might also involve certain other constraints in terms of some application. A vendor might be able to look at it and say, I don't want to use certain hardware resources. I want to only use, let's say, only GPU. I don't want to touch CPU because I have CPU busy for doing some other task. So application should be able to specify those constraints using some kind of a hints at a very top level, right? And that gets you to an implementation to start scheduling a particular workload. And the second part is memory management. Given that we specify a graph and every object, data object is kind of some kind of a abstract object, if there are a lot of several intermediate buffers, it doesn't, an implementation, OpenVX doesn't have to allocate all the buffers, so what can it do is it can just allocate a couple of buffers and try to reuse them because they're all intermediate buffers, application doesn't need it. So it kind of gets you a better memory allocation. And this memory allocation might not be in the space, in the host space that application has to access. For example, if I have a complex hardware where I have some kind of internal memory, it could be a GPU private memory or it could be a DSP local memory. So these buffers can be allocated depending on what the underlying hardware has. That's this kind of second level optimization that you get. And the third one is kind of a kernel fusion. I think one example I gave earlier was a color conversion. That's kind of a very simple example. The way to think about it is, I think one example that Ralph has noted is about fusing some of the kernels. I have one example that I use is I have an OpenCL-based implementation on the AMD's OpenVX is open source. You can look at that. So one example I have is a skin tone detector, which is basically a bunch of comparisons. Kind of you look see if R is greater than a certain threshold, less than some threshold. So you can describe that in OpenVX using the standard set of flows. It will take maybe around 10, 12 nodes to describe that whole description. Now an implementation can look at that whole flow and generate one OpenCL kernel. It can go to the extent of, since there is only bit level operations done, comparisons done, it can map it into even a 1-bit level of data points and can fuse all those kernels into one. So you can, another way to look at this is you can think of it as a memory management, but where here memory is going to become a register. And register can be of type depending on what functionality you kind of described in the graph in there. And the last but not least is looking at the locality of the memory, so tiling. We all do this when you try to look at it from an OpenCL. You kind of use a local work group. You try to hand optimize at an application level. But when it comes to OpenVX, user is going to specify at a high level what is the functionality they need. If they want to run a filter followed by some other kind of functionality going through, now an implementation can look at it and say the whole pipeline is data parallel up to this path, and it can just say, I'm going to pull up part of the data that fits into the local memory or whatever it is and run the pipeline to how far it can go, and then kind of pull the next tile, go through it. So an implementation, basically a vendor gets a choice to look at the whole graph, try to do a lot of optimizations, which is otherwise a lot of overhead for an implementer to do, an application developer to do, sorry. So here is a simple example of edge detector. This is not 100% syntax, but it kind of gives you the concept in here. First, basically, you create a graph, and then kind of declare your inputs and outputs. You can kind of see here, you have a 1080 image as an input and an output, and then you declare a bunch of intermediate data. So what it is doing here is constructing a graph, taking an image, running a Sobel 3x3 filter, and Sobel basically gives you horizontal and vertical gradients. And then it's kind of computing a magnitude, just kind of a L2 norm. And then using that magnitude of the gradient, it tries to do a threshold, and the output is kind of goes into just kind of 0 or 1. You can think of it that way. You can kind of see where the strong edges are. So the way to construct is basically you just specify 3 nodes, and you have H, V, and M as intermediate data objects in there. Then once you construct a graph topology, then all you want to do is you want to compile a graph. So the one way to do that is there's an API called VX Verify Graph. This is a place which kind of looks at the data consistency, see if there are any cycles and any of the issues that are there. And this is a placeholder for an implementation to look at the graph, try to compile the code if it needs to do any code generation. If you're doing an underlying platform is OpenCL, you can do a code generation. If it is a DSP or CPU, you might pick which code path you want to run, things like that. And once you have a graph compile, then that's a part that kind of probably takes a little bit offline, or maybe may not meet the real time of whatever milliseconds that you have if you have a real-time data coming in. But the execute is the one that's going to get you real-time. It is all optimized to the constraint that an application specifies and runs the frame as quick as it can, depending on the constraints that the application specified. Now, let's look at the various versions that we have released so far. We have released 1.0 in October 2014. That's kind of we aligned. We did a workshop at CVPR that time, kind of we aligned it. And every year, now the goal is to release a new version coming up. The last one that we released is 1.2 this May at Embedded Vision Summit. We released. The key features that we added in here is kind of a conditional node, which basically in a graph you can specify which path to take. Basically, if you have multiple cameras coming in, if you want to decide to some kind of a criteria which path to take to execute, you can specify that path in a conditional way. And the challenge always is when there's a conditional execution, we have to support multiple kinds of hardware going from DSPs to GPUs to CPUs. How do we specify it in a way that can get translated to all the different kind of hardware? So we kind of use something called a select node we specified. So you specify data path, at the end you specify a select node, and depending on the flag, it kind of picks which one it is. So it gives a mechanism for an implementation to look at all the paths that are possible, pick the one that is going to execute for the optimal performance coming through. And a couple of other things is we added feature detection and classification, and we added a couple of more image processing operations in there. In terms of extension, the big one that a lot of people are interested in is neural network accelerator, and primarily focusing on inference. So if you have a network that is pre-trained, you can take those weights and try to build an OpenVX network, a graph, that people can take it and map it into their hardware, depending on whether it's a DSP or GPU or even CPU, and all those things are possible. It is primarily designed to be real-time and low power. That is the primary goal that we have when we designed that. And for safety critical, we added a feature to be able to take a graph and compile it offline, generate a binary. So I have a graph that I have a slide that will show you how that whole thing works. But the key feature is so that you can kind of separate out offline processing of building a graph, compile it for a particular hardware, in safety criticals, you don't want too much code. The danger of having too much code is now a vendor has to go through a lot of verification. It's going to cost them a lot going through the safety critical process in there. And in terms of, you can kind of see there are various companies who have made their implementations of OpenVX, and they're all conformant, and you can see the huge list here. And there is one implementation of OpenVX, we just kind of open sourced that part. You can kind of look at it on the GitHub. Now going forward, what we have coming up is NNEF import is one thing we're looking at. So once you train your networks using TensorFlow or Caffe or whatever it is, we want to be able to import that into OpenVX. So we're kind of trying to make sure these two standards are going hand in hand together. And the other part is being able to allow users to extend the functionality of OpenVX kernels. We have certain functions available if a customer wants a particular vision function that is very specific to their need. Right now, the only way they can do it is create a node that runs on the host. But I think there's an increasing need. A lot of people want to be able to express that in a accelerated on a particular hardware. It's a big challenge because we have customers who are pure DSP to somebody who has GPUs sitting in there. So we're still working on that problem, trying to figure things out. Another part that we're looking at is streaming and pipelining. If you try to look at the real-time scenario where you have data coming in from a camera frame by frame, let's say after every 30 frames, you want to be kind of push data out. We need a mechanism to be able to queue up. Right now in 1.2, only API we have is VX process graph, and just lets you give a call, it processes it and comes back. Instead of that, we want to provide a model where you can kind of create your whole pipeline as multiple stage and feed data through the whole pipeline, like a multi-stage pipeline you can think about. So I went over a lot of these features in here, key parts. Probably I'm going to skip in the interest of time. One thing I want to mention here is an example for the conditional. You can see, let's take a graph where you have a node A, which gets 2 data output. At the end, you want to select which one you want through some functionality, some other processing you want to do. You want to pick right or left. Where this is useful is in the first example where I gave, let's say you have a set of people walking, and you want to kind of track people using features. So initially, you start with running some kind of a Harris node. You have initial set of features. After that, you want to use optical flow because that's very efficient at tracking. And after some time, you kind of lose set of features. You want to kind of refresh the whole thing. That can be done using some kind of a select. So that select can be triggered once in, let's say, 10 frames, 100 frames, or even you can look at number of features that are there. You say if it goes below a certain threshold, let's say 80%, I want to run Harris. So all those kind of use cases can be available using the conditional execution feature that we have. Neural networks is an extension that we have. I'll cover that in a couple of slides that I have. In terms of feature detectors, we have added histogram of gradients, template matching, some kind of half-line for line finding, and LBP. These are kind of some new features we added. We're still looking for some feedback from the application side to look at our current features that we have and see if there is any features that they're really interested in. Key challenge for us is we have a variety of platforms. If we try to put some feature into our hardware, we want to make sure it is supported across by all vendors, and that's always going to be a challenge. So we kind of have a minimal set of features that we picked that are common across all the vision applications. But if there are particular needs, we would like to hear that and try to figure out a way to address those needs in our OpenVX roadmap. So OpenVX neural network function, how does it look? Basically, you can kind of take a neural network. It's made up of a bunch of layers, things like convolutions or local response normalization, what else? Pooling, activation, softmax, things like that. So we have a separate call for each of those nodes. So you can kind of create a graph just the way you have it in Caffe or NNEF. You can kind of, I have one intern who was kind of looking at Caffe. If you take a Caffe model, being able to export that straight into an OpenVX framework. And at Embedded Vision Summit this year in May, we have demonstrated one use case where we took a Caffe model and we ran it through Intel's CVSDK. They have one model where you can take a Caffe import and then generate an OpenVX code directly that you can run an inference on. And that was a good example. You could probably look at our embedded Khronos website to look at the tutorial that we have posted, all the source material in there too. And what else? And we have import and export extension to be able to import the weights coming from there, because there, we have this concept of tensors for multidimensional object. So you can kind of take this data, you can write a tool to export them into some kind of a binary and then import it for real-time consumption in there. If you look at the diagram below here, you see one advantage of OpenVX compared to a dedicated inference engine is you have the flexibility to kind of combine both vision processing as well as neural networks as kind of one part into it. So imagine you have a data coming from a camera, you want to do some kind of pre-processing, and then you want to feed that pre-processed output to a neural network, and you want to take the output and do some other processing, depending on what are the logic that you might have. You can kind of take that and then basically you have a flexibility to combine both classical vision as well as neural networks into the same framework. And that's a pretty advantage. Now this slide kind of mentions you about, let me see how much time I have. Okay, I still have time. So tensors, you can specify one-dimensional tensor or a two-dimensional, up to 4 dimensions we support. So it kind of supports the CAFE, most commonly used topologies it supports. And the basic for math functionality on tensors we support are kind of, you can do element-wise operations in terms of bit conversions or things like that. You can copy. You can do general matrix multiply. Kind of a lot of people ask for jump these days, and we have that functional API added for that. And there's a transpose. Certain cases, you kind of take it existing tensor, you want to transpose it, pass it through matrix multiply to get some kind of other functions, such as if you want to do some kind of a deconvolution, things like that. Now, how does the API look like, and what are the various data types our OpenVX neural network sections support? What we mandated is everybody should support 8-bit data types and fixed point 7.8, Q7.8 format. Those are kind of mandated if somebody wants to extend it. For example, if somebody wants to extend it to support floating point, it's up to the vendor. But if you write your application to make use of these data types, you can be sure that everybody who claims support of OpenVX, your application will run across all the vendors. Right? And the mapping of nodes is kind of very straightforward. We kind of pick the name so that it's kind of obvious. If it's an activation, you put VX activation layer, kind of takes an input tensor and an output tensor, and you specify what kind of activation it is. And similarly, convolution, pooling, normalization, fully connected layers, all these names kind of one-to-one mapping with CAFE. If you're familiar with CAFE or any other existing frameworks, you'll be very familiar with OpenVX naming convention there. And one of the things we had to do when it comes to conformance is kind of, it's very tricky. How would we specify the conformance when somebody claims conformance? So what we did is we kind of tried to specify some kind of a tolerance for each of these layers, or basically every function, and then every vendor who goes through these tests guarantee that you get that kind of a precision available. So in most of the cases, you have to run through it and make sure it kind of conforms. Kind of we made a compromise on what tolerance is acceptable to all the members of the working group here. Safety critical spec, I think we have the standard OpenGL, and so I'm gonna skip. Okay, for OpenVX, we released a safety critical spec in the May, and for safety critical, what we have is we restricted this safety critical spec to just the deployment part. That means you have already taken a graph, you pre-compiled it, you exported it into some kind of a binary. The part that is that is included in the safety critical part is just the deployment. Being able to import a binary and then run it continuously. Being able to create an image or a tensor as an input and then pass it to a graph that is pre-compiled. That's the only part. That is very essential because we want to reduce the amount of code that somebody has to write and take it through the safety critical process. And I think Neil has touched upon this. We have the TSGs for safety critical on OpenCL. And there's a Khronos safety critical advisory panel that is, I think it's recently started, right? And we're looking for more members to come and participate in that. And yeah, here is an example, kind of an overview of how the flow looks like. You have a development feature, which is the standard OpenVX feature set that we have. And once you create a graph and export it, you get this binary blob. You can think of it as a binary implementation. The safety critical deployment feature set, the part that executes, that is the key part of the safety critical feature. We made sure all the header file have passed through MISRA-3 just to make sure to kind of help implementers to take it through the safety critical flow. And our current safety critical spec is based on 1.1. The reason is most of the time, once a spec is out, it takes some time to go through it to make sure there are not much overheads in there. It kind of complies with MISRA-3. It takes some certain kind of steps to go through it. So we kind of always tend to be one version of the spec behind on the safety critical. We're hoping to release 1.2 at the time of the next OpenVX specification. Now, this is one question a lot of people ask who are beginners to OpenVX to say, how does OpenVX compare with OpenCV and OpenCL? This kind of question comes back. So OpenCL, OpenVX is easy. I think our earlier speakers have kind of compared with it. OpenCL tends to be very low level. User get a chance to specify how to schedule everything. And user has to specify how to write each function at the lowest level. Whereas in case of OpenVX, its application vendor takes care of it. And they might not write, they might use OpenCL. Some might even code it in assembly to get the peak performance coming out of their hardware. Now, when you try to look at it from OpenCV, the big difference here is OpenCV is a huge code base. It has evolved over a decade and all, longer than a decade. And it has thousands and thousands of functions. That's a good thing about it. It's a very good prototyping tool. People can take it. If they have some idea in mind, they can just quickly take and prototype it and check that their application is running. But when it comes to performance, it's kind of a function call basis. So you don't have the flexibility to be able to fuse the functions that easily. A vendor cannot do it. So you have some kind of a performance overheads that one might hit an issue here. And another one is, another disadvantage there is for conformance. If you try to take an implementation of OpenCV on, let's say, DSP, somebody took the same code base, tried to customize it to their DSP, they have to go through certain kind of functional compromises they might make. And when a user, when I write an application, will my application run on all the DSPs and all the CPUs and GPUs? Again, there's no conformance program. So there's no one person sits and says, yeah, your application will run seamlessly across all the implementations. That's not guaranteed. And that's one of the key features of OpenVX. Once somebody says they have OpenVX implemented, you can be guaranteed that your function, your application will be functional portability will be there, performance portability will also be there in that. What else? Our functionality, we're trying to slowly increase the functions that are needed. Right now, we don't have all the functions that OpenCV has, but we're going to keep increasing it depending on the feedback that we get from the industry. And what else? So coming to I think it's almost close to the last slides. So what OpenVX gives you is a fast development and portable code because you're kind of specifying your functionality at a very high level. And we have a lot of optimizations possible in terms of kernel fusion and tiling on diverse hardware. And I have a couple of links that I provided here. You can go to khronos.org/OpenVX. There is a registry where you can look at our specification. One link that's not present here is you can go to our forum. I see a lot of people posting their questions. If you have any questions about OpenVX or if you want to see new functions that you want, you can send an email to Neil or me, or you can post it on our forum on the Khronos. So some of the working group members will keep monitoring. They'll post a response to you on that. Now, you probably have seen this diagram before. So you can have an application layer on the top, you can kind of see when an application tries to map their functionality into OpenVX, OpenVX basically looks at, it can use OpenCL or Vulkan, or it can look at the dedicated hardware functionality. So we have a roadmap right now for trying to standardize OpenCL and Vulkan as a means to be able to accelerate for, especially if you have a custom functionality to support. Right now that is not functional. There are some vendors like AMD and Intel for sure. I know they used OpenCL because it's kind of public information in there. So we're trying to figure out a way to add means to allow users to extend the OpenVX functionality by writing in Vulkan or OpenCL. What else? That's pretty much it. That I would like to hand it back to Neil.
Right, we have just a couple minutes for questions, if there are any. We have all the speakers here, so they know what they're talking about. Yeah.
I'm not sure if it's this use case for OpenVX, but building the adoption, that's what I wonder if there is having a node. Sorry. I wonder if there is a goal for having a node where you could specify SYCL kernels. And then go through the graph, even if it's not the best performance.
Let me repeat the question, make sure I understand it correctly. So you're saying if there's a graph, a user wants to specify their functionality in OpenCL and being able to inject into the graph, is that the question?
Yeah. SYCL.
As a SYCL?
Yeah, SYCL.
Okay, SYCL and OpenCL. So we haven't looked at that yet, but probably I'll let Ralph, did you get a chance to look at the interop between SYCL and OpenVX?
I haven't.
Okay.
The answer is we should look at it.
We should look at it, yeah. But OpenVX does have a mechanism right now where you kind of you can specify a user functionality as a host function. And AMD has taken path of, we extended it by putting another call, which will basically provide a user can extend their application where it will return an OpenCL kernel, the source. Basically, it can provide a source, and the underlying OpenVX framework will take care of compiling it and putting it into the pipeline. But when it comes to SYCL, now, the way I see it is OpenVX try to be a master, trying to take control of the whole application. And SYCL has the same paradigm. SYCL wants to be the master. Now we have to figure out a way between these two masters how to cooperate with each other. That's something we haven't figured that out yet. But if there's a use case, we'd like to hear that and add that to our roadmap. Thank you.
It's a related question.
Could you just pass the mic over so the folks online can hear? Thanks.
A very related question. So I want to precise that about SYCL. When you develop, it's very nice to be able to update kernel on the fly. So I understand that SYCL have to look at the content of the kernel to be able to compile the graph. So that means that you have to compile and go back to where you were every time?
So you're asking about
compiling on the fly OpenCL kernel using SYCL.
So you're asking about kind of runtime construction of a kernel. So SYCL directly isn't going to give you that because SYCL requires this kind of full compilation. We're going to take C++, which is quite a heavy thing to build a compiler for, compile it offline into some intermediate format and bring it back in. The one thing you can do there is because we have interop with OpenCL, what you can do is build an OpenCL C kernel. Everything you can do with OpenCL C, you can still bring into the SYCL scheduler. So you can build an OpenCL C kernel. SYCL provides you the APIs to compile that OpenCL C kernel, and then you can hook that into the SYCL scheduler. So you can still get all the kind of automatic data movement and all that sort of thing, but to actually build the kernel, you would probably have to do it in OpenCL C just because the SYCL compiler itself is an offline process.
Okay.